Okay, welcome back. So in today's class, we talk about numerical linear algebra. And I'll do a small review about basic facts on solving linear systems where AX equals B. So mainly in this talk today, I'll talk about systems of equations and Arnoldi vectors and eigenvalues. The talk is going to be short because I have an online quiz just after the class with a calculus 3 group. So I'll let you go probably maybe 10 or 5 minutes before the end of the class. So hope everything is set. I can start. So I'll do a small review about the fact that solving the linear system where AX equals B. Hopefully you can see my drawing on the slides. Can you?
Yes, we can.
Yes, we can. Yes.
Yeah. So usually, what happens if A is squared? If A is squared, I mean M by M, for instance. How do you solve this this linear system? Just a small, quick review, guys.
Row reduction.
Power reduction. Well, what do you mean by power reduction?
I mean row reduction.
Okay, so because you said one typical word, which I mean triggered me. Okay, so row reduction, but in the case the matrix is squared, like M by M, and if the determinant is non-zero, what can you do?
Inverse.
Yeah, so basically in that case, X is equal to A inverse B, right? In all cases. Got it? Well, there is one common fact, is that in that case, in that typical case, well, you can construct a series of submatrices of A. Do you know this? Or submatrices? In fact, they're not exactly submatrices, but parent matrices. We can call them, for instance, A tilde I, where typically in AI, it contains the same columns as A, but you take, so for example, you take the same columns as A, A1, A2, but when you reach column I, you place B instead. Okay, so, and you continue AI plus 1 till the last column, which is, as we said, we have a size M, so we reach. Got it, guys? So typically this submatrix has been obtained from A just by taking one column. Which column, guys? Column I, okay? So AI is removed. Okay, got it? And replace it by whom? As we said, we replace it by B. Okay? Now, why are we doing this? Well, it's a kind of shortcut on how to obtain this X, in fact. In fact, what is said is that the solution in that case, in the case where A is invertible, is equal to the following. Xi would always be equal to the determinant of A tilde I over, guess what? Determinant of A itself. Okay? It's a very common and beautiful fact about the solution of square systems, in fact. My point, why am I saying square systems again? Because I'm saying that this matrix is square, M by M, which means that here I have M unknowns, okay? And here I have M right-hand side, okay? Did you know this before, guys? basically, this gives you, when you arrange all of these items together, this gives you basically all exactly the same formula we had before, where x equals a minus 1 inverse b. Exactly this. Okay, which is kind of a beautiful thing about solving linear systems. So the fact that we can still learn about solutions of linear systems, and as one of you, maybe Khalid, said, we can always solve using row echelon, one may wonder what happens when we have very large systems. What happens when you have very large systems? When you have tens of thousands of columns and conditions? Are you always going to continue to use the row echelon matrices method? Or are you always going to try to find the inverse of A? What happens, for instance, if you have very sparse matrices like A? So these are the questions that are raised when we talk about big data, and typically these are the problems that attract our attention in numerical linear algebra. Okay, so can I go forward, guys? Is that clear? I can give you a small example if you wish, just to show you that it works. So I'll share with you just a simple whiteboard, and hopefully everyone would swallow this properly. So let's say, for example, I have this very easy problem. I'm taking a matrix for which I can define an easy solution. Okay. So this is A for me, and this is B. Okay. B is 4, 3. Got it, guys? Okay, beautiful. So what do you notice? A is squared, so it's a 2 by 2. Okay. Secondly, more than this, it's an invertible, right? So the determinant of A is how much, guys? It is 1 minus 6, which is -5. It's not 0. Hello, beautiful. So what the typical way to do it is to find x as just A inverse B, right? Because it's a square system, and we can just apply the new method of C. So for here, I'm going to have x1 as 4, 3, 3, 1 determinant, divided by the determinant of A, which is -5. And x2 would be the determinant of whom? Of 1, 2, 4, 3, divided by -5 again. Okay? So here I applied my rule, and let's see what we get. So typically here I'm going to have 4 minus 9 above, which is -5 over -5, right? The determinant of this first matrix A tilde 1, this is A tilde 1 inside, guys, huh? And this is A tilde 2. So this is equal to how much? The first answer, Shabab, first variable, 1. Second one is, as you can see, is 3 minus 8, which is -5 again, over -5. I'm well set, I have 1, 1. Okay? I can see that 1, 1 matches the answer, so because 1 plus 3 equals 4, and 1 3. So, well, the setting of the columns and the rows is well done, so I have an obvious answer, which is 1, 1. And you can see that here I avoided what? I avoided entering the misery and suffering the misery, for example, to look for A inverse. You get my point, guys? Okay. Well, looking for A inverse would give you the same, of course, same answer here for a 2 by 2. It's not that problematic. You would have done exactly what we usually do. It's A minus 1, which is -1 over 5, because I have to divide by the determinant. And here I'll get what? I'll get 1, 1. Here in this position, I'll get -3, am I right? And here I'll get negative 2. Okay? So basically, this is A inverse. Yani you would have already a fractional matrix, which is not that well to deal with, not that, aesthetic to deal with, but you will have to multiply it with A inverse with B. So A inverse B would be, again, how much? Here, minus 5 times 3, minus 1. I have minus 4 plus 9 over 5, which is 1. So I get 5 over 5. And here I get, again, I'll have 8 minus 3, so it's 5 over 5. So I get the 1, 1. Guys, see it? Okay. So, but even though this is interesting, because this way we can avoid inverting matrices. Okay? But life is not that easy. Okay? Got this, guys? So let me switch back. It works all the time when we have square matrices which are invertible. It works all the time. But the issue here is that maybe we're not that able to invert matrices anymore. Okay, so I'll go back to my screen. Line 5, sorry. So I was sharing with you the first slide of our lecture for today. And as I said, today we talk mainly about these kind of issues. So what is the idea? So when the matrix or a tensor is really large in the data, we'll often have to sample the matrix. What do you mean by sampling the matrix? I mean, taking chunks of it, separating it. Okay, this section summarizes the central ideas of classical numerical linear algebra. Well, it may seem impossible, but that random sampling would give a reliable answer. Okay, but in fact, this is highly probable, and it works. The aim of this sampling works to solve our first issue, which is solving a linear system, AX equals B, or solving the eigenvector problem. Remember, this is the setting of the eigenvector problem. Huh? In this case, we call it the sigma problem. Right? So our goal is to outline important iterative algorithms from that to solve systems of equation or compute eigenvalues. This should be to solve. Huh? Sorry for the misspelling. So let's move forward. So the first idea here, and I will show you how to do it computationally. So this is the advantage of having a very useful tool like Python programming. So what are we going to do? We are going to build a model for the iteration where we split the A coming from AX equals B. Yeah? We split it in two parts, a matrix S and a matrix T, where we do have A equals S minus T. So the linear system, which was AX equals B, becomes, if you just write S minus T instead of A, you obtain this matrix, this system. Sorry for that. So the idea is to start with any given x0, okay, and to iterate where we could, with a given x0, we compute the x0 plus b, and we try to find the x1 that would solve the new system. Okay. Of course, now the inspiration is to get a hand on the right choice of S and T that would allow you very easy convergence. So the right choice of S and T to increase your convergence probability and its speed is to make the choice such that the norm of S minus 1 T is less than 1. We continue then with the new x1 we found on the first iteration. We place it as a new parameter in the next iteration to look for the next two. So what is said is that if S is chosen, each step itself, because you are able to exploit the structure of your S you chose yourself. So you choose it in a way that this iteration is quick and fast, and it allows you easy and fast conversions. And it's very common that iterations take a couple of hundreds of iterations to reach stability. Stability means that, well, you have exactly that is the same solution xk or xk plus 1 that is stable, that is repeated. Okay, so subtracting in that case, when you reach, for example, stage k plus 1, when you subtract sxk plus 1 from the exact system you had before, after splitting the matrix A, gives you what we call the error equation. And what you want is, in fact, to minimize your distance, the distance from your xk plus 1 to x. So, in fact, if you multiply both sides here by S inverse, what do you get? You get x minus k plus 1 equals how much? Equals S inverse t times x minus xk. That's why we say that at every iteration, the previous error is multiplied by S inverse minus t. So at every step, multiplies the error by S inverse minus 1t. You get it? Okay. So let's show you. Let me show you how to do it numerically with Python. Okay. So. Let me share with you my screen, first of all. One second, please. Okay, so here we go. So as you see here, I kind of arranged to program this this algorithm in a way that we could compute an easy solution to a given problem. So in our case here, what do I have? I have well, this should be previously defined. Okay. Type. Well, I have defined my matrix A to be negative 1, 1, 1, 1. So it means I have a 2 by 2 system. B to be 3, 5. And I'm just making sure that T completes the fact that we do have S equals A plus T. Since we said that A minus T equals S. We said that A minus T, that A is equal to S minus T, which means that, in fact, A is equal to S minus T. So we do have S as A plus T. Okay? Here, in this stage, what am I doing, guys? I'm asserting that the matrix which I generate, which is equal to S inverse times T, has a norm which is, I want to print its norm. I want to know if its norm is less than 1, okay, or close to 1. You got it? Why am I doing that, guys? To make sure that I would converge quite fast. Then I'm entering my loop. I'm initializing my xk to be 1, 1. So basically, I'm starting for an initial solution. As they said in the algorithm, we start from x0. So this is our initial x0. You got it?
Doctor.
Yes, Abdulaziz.
What do you mean by S inverse times T? What does it represent?
S inverse times T is the multiple which we use to judge whether we are reducing the error or not. I mean, the target we want to reach is the exact solution to our system, right? But at every iteration, what we hold in our hands is a vector xk, right? Which comes out of the kth iteration. So S inverse times T is the matrix that allows to converge faster or not to the exact solution, as I was posing in slide Ablaziz. I'll come back to it. Okay, I just show you how to run this, and I'll come back to it. So once we obtained, we've set our initial solution x0. We just have to code this iteration here, where I just have to do what? I have to perform just the inversion, where the new solution equals to what? It's equal to the inverse of S times the matrix which we obtain, which is Tx plus B. So I define L to be Tx0 plus B, your initial solution. And I make sure that the new solution I obtain is S inverse times this matrix L. Okay? And at every iteration, I'm going to have a new solution. So let me run it with you to see if it works or not. And let's share. Hopefully you see yeah, it's okay. It's appearing here. So it takes a little bit of time. More time than usual. Okay, there might be something wrong. I don't know. Let me just restart the project from the beginning and see if it works. Sorry for that, guys. Should be coming. Very slow. So I'm trying to close everything that is running. Let's stick to this. It should be loaded. Okay. So I'll stop sharing. I'll come back to it when it loads. Okay. Let's move from the other side. Like we were here. Okay. So this is what I wanted to show you. In fact. So this is a case. Yeah, Abdulaziz, are you still with me? Okay. It's finally loaded. I'll come back to it. So this is, for example, I have a 3x3 system. Okay. So here I'm splitting A into two matrices, S, which is, as you see, beautifully chosen to be diagonal. Why am I doing this? This is the diagonal matrix where it's very easy to compute not only the determinant, but also the inverse, right? Okay. So what is left from that is to find T. How much is T? We said that A is equal to S minus T, right? So T is just the completion where T is equal to S minus T. Got it? So here I've chosen myself S to be 50003006. And I start with the initial vector 1, 1. So with the Python 5 I will upload, we show how to run this algorithm. So in that case, you see that the norm of S inverse times T, when you apply the multiply this to the inverse matrix S by T, you get a norm of 1.332, which is quite close to 1. Even in this case, we see that after a couple of iterations, we converge to the exact solution to this system, which is 1375 minus 1 and 2625 after about 50 iterations. But in general, having this not larger than 1 might be problematic and cause probably divergence. Okay, so the main difficulty here lies on the right splitting of A into two matrices S and T. So just try to run it before I show you. Okay. So I'll share with you again my my screen and show you how to run this. So it's working now, so I can share it with you. Okay. So here, what I did, I just ran my my algorithm. I've shown you. You see the screen, right? So here, I was still back to the previous system where I had 1, minus 1, 1, 1, 1, and just 3, 5, okay, as right-hand side. Are you still with me, Shabab? So here, I'm displaying just the details of the iterations at every time. So for instance, the first matrix I obtained, in that case, I'm in a 2 by 2 case, when I made this separation where t is equal to, I said negative 1, 1, I'm reading here, okay? When I made this separation where t is equal to negative 1, 1, 1, 1, I obtained the matrix S, and the S inverse times t, S inverse times t gives you this matrix, and you see the norm is less than 1, okay? So I'm pretty sure from this setting that I will converge quite fast. So if I enter with x0 equal 1, 1, and I do my computation where I multiply to obtain the new x, I multiply tx plus b by s inverse, right? I obtain the new solution, which is here, 1, 2, 5, as you see. And the next iteration, I initialize. Yes, sir.
Sir, but can you repeat the second iteration? I didn't understand what you've done.
Okay, here in the code or in the display?
In the code.
In the code, okay. So in the iteration, I entered with x0, right? I'm here.
Yes.
So I'm using a temporary variable, which is xt. I'm calling it xt, which takes the initial variable with which the vector with which I enter the loop. Are you still with me?
Yes.
Okay.
Yes.
Because this is the xt that's going to be updated. Now I compute a new matrix, which I call, as you see, txt plus b. Yani, initially, when I enter with x0, this guy is going to be what? This guy is tx0, txk plus b, right?
Yes.
Okay, I get it. So I'm just casting in this whole matrix txk plus b, t times xk plus b. So I refer to it as L, okay? Now to find the new k, all I need to do is to multiply this matrix by just S inverse.
Oh, okay.
So this is what I'm doing here. To find the new xk, I multiply S inverse by inverse of S by L. I get the new xk. Of course, since I'm saying that I'm looping, I'm repeating it from I equals 1 to 25. Next time I enter the loop, when I equals 2, I use xt, which is given by the last solution. So here, I update my temporary value. So for here, xk plus 1 becomes xk in the next stage.
Okay.
Did you all get it? Okay.
Yes.
So, okay, beautiful. So when I entered with, for instance, here, when I entered with 1 to 5, next time, I'm feeding 1 to 5. This is the initial solution. Okay? You see my mouse, huh? And I multiply, I get the new solution, 1, 3, 2, 5. Okay? And after a couple of iterations here, I'm just displaying 50 iterations, which is a lot. In fact, it converges quite fast to the right answer, which is about 1, 4. The right answer is 1, 4. Get it?
Yes.
Right? Of course, I did not need to do this for this 2 by 2 problem. Okay, but I'm just showing you how to implement this. For example, in this file. So that was the 2x2 file I will upload. In the 3x3, of course, I'm adapting the size of my initialization, and that's it. But the core of the algorithm is still the same, okay? And I will obtain exactly the same result I've shown in the slides. Okay? So this is the example I was detailing in the slide where I had this 3x3 matrix. The S, which was diagonal, and the B vector, which was 3, 2, 4, and iterating, I will reach my solution. Got it, guys?
Yes.
Is it okay? So this is the implementation. Well, you see, we can go forward. We can, in knowledge, we can learn new things. So we can imagine that if your choice is right and you have the right splitting of your matrix, well, you probably could be able to solve a system much faster than by matrix inversion. I mean, by the whole matrix A inversion, because now you are choosing properly which matrix to convert, right? And not A. You get my point, guys? And as we've seen it, even analytically, this is possible, in fact, if you have an invertible matrix. So where was I? Well, I was here. Okay? And now I'm going to move forward a little bit. And hopefully, I'm going to stop in about 10 minutes. Okay? And now that we've talked about solving linear system, I'll talk about now that we have to wonder what happens if we try to solve the problem of finding the eigenvectors. Okay? But we have very large matrices. Remember, finding the eigenvectors itself is like solving a linear system. You remember, guys? Every time we solve it, we try to find the eigenvalues. We solve the polynomial, which has been shown, in fact, a long time ago, that solving polynomials and polynomials analytically is something that is impossible. Okay? I mean, analytically reaching formulas like the ones we have for second-degree polynomials is impossible. It has been shown a long time, like about 70 years ago. But finding the eigenvectors corresponding to these eigenvalues is a problem itself. In fact, it is parent to solving what? To solving a linear system. Because once the lambdas are set, you obtain a new system, in fact, every time. So an intuitive method for finding the largest eigenvalues. Now, if you've been following us the last 5 weeks, if you've been, body and mind with us the last 5 weeks, why do I have to look for the largest eigenvalues, guys?
Because it captures most of the original matrix.
Exactly. Thank you very much, Mohammed. So because the largest eigenvalues, they capture most of the data or information that is in the matrix itself. Now the question, why do we have to look for all the eigenvalues if I can have the largest ones, and the largest one are quite representative, so they give me a good approximation. And this is the way we tackle problems in big data or in data science. So now we focus on this problem. Remember, this is our problem now, finding the largest eigenvalue for a given matrix m by n, which quite reminds us what we've been dealing with the solution of linear system. We perform what we call the power iteration. So remember when one of our colleagues here, our classmates, said row echelon, and I quite heard power operation. He said row operation, and I heard power operation. I was stuck because this power iteration, in fact, we define here. We start by a vector b, which is not parent to the one we had as a right-hand side in the linear system. Okay, not parent at all. Just like an x0, an initial seed for our iteration, and we calculate the following vectors: ab, a square b, a cube b till a minus 1. If you count them all, b till a n n minus 1, I have how many ones? I have n. Okay? In fact, if the matrix multiplication A, B is fast, this matrix multiplication, sorry, is fast, particularly if A is sparse. Oh, so that solves part of our problem. Now, what is the deal? Why do I have to do this? In fact, when we do this, we are trying to project A, which is m by m, into a new space which is of dimension n. Okay? We move from a space of dimension m to a space of dimension n. And this typical space, because I have here how many vectors? I have n vectors, right? And why do I have to do this? Because I want to reduce the size of my problem to be able to find the largest eigenvalues. Okay? In fact, the sequence, what it says is that this sequence converges to the eigenvector corresponding to the eigenvalue of the largest lambda 1. It has been shown by Krylov and others that this sequence, in fact, when you do this multiplication or this power iteration, you converge towards what? The eigenvector with the largest eigenvalue, which is beautiful. And the combination of these n vectors we've mentioned, they define what we call the Krylov subspace, which containing n vectors. Now the problem is that you are trying to project an m-sized problem on an n-sized space, is that you don't have the combination of these vectors. These vectors are not, let's say, orthogonal, and not even orthonormal, okay? Because what is needed to generate a space is perfectly would be a set of an orthonormal basis, right? Am I right? But in this case, there is a problem, is that the vectors you get here are not always orthonormal. So there is a trick to overcome this, and the trick is to do what we call the Arnoldi iteration. Okay, now just to put you inside the bath again. In the bath again, we are looking for the largest eigenvalue for the large matrix, okay, that is possibly sparse. And as Mohammed said, we are doing this because we would like to extract the most part of the information in this data matrix. So we look inside this subspace Kn, we call it for Krylov K, for a close approximation to the desired solution eigenvector, okay, which is corresponding to the largest eigenvalue. Now, Mohammed, can you continue? If I have the largest eigenvalue and the largest eigenvector, basically, I like the largest, the closest approximation to my matrix. You get my point? So the first problem is to find a much better basis than those vectors which are not orthonormal. Okay? And the best way to do that is to define a new basis, Q1 to Qn, and we'll do it by what we will call the Arnoldi iteration. Okay? And one way comes from Gram-Schmidt's idea, which is the subtraction of the projections obtained by A times Q every time to obtain these orthonormal vectors. So remember, we are looking for now a new set of vectors that do define an orthonormal basis to our Krylov space. Okay? So I will stop here today, okay? And I'll show you next time, inshallah, how to perform the Arnoldi iteration. And I already implemented the code to do it. And hopefully you will enjoy this. So I'm here because I have another quiz, guys, with the Matu and Gaze guys, and I have to get them seated. Any question before we leave? Please think about any question you have. So we said our first assessment would be next week, right? The 13th. Don't forget, huh? Yes? Right. Since I've seen that not everyone is here today, I'll take the attendance just to make sure that rules are rules for everyone and nobody is missing classes for no reason. So Abdurrahman, Muhammad Abdurrahman. موجود؟
محمد عبد الرحيم دكتور. Yes, present.
عبد الرحيم موجود. Yes. عبد العزيز السنبل.
Yes, doctor.
Sultan. العبودي، خالد البديع،
Yes.
حسن بن سعد، حسن، عبد الإله الفرج،
Yes.
فارس الحسن،
Yes.
عبد الرحمن الحسين،
الحسين. Yes.
نعم، محمد الجلود،
Yes, I'm here.
عبد الله العيني،
Yes.
ثامر عتيبي، ثامر، عبد العزيز الراشد، فراس الرميخاني.
Yes.
وينك يا فراس؟ عبد الله رقيع،
Yes.
حاتم رويس، نواف الشهري، نواف، فيصل السبيعي،
Yes, doctor.
عبد العزيز السليماني.
دكتور في إسامة العتيبي كتب
نعم.
بالشات يس.
اوكي طيب، عبد العزيز وينه؟ سليماني مش موجود. يوسف بنتن كان معنا. عبد العزيز غريب. يوسف بنتن موجود؟ كل الشباب راحوا ليش؟
يس دكتور، معلش
اسمعوا.
صار مشكلة اتصال.
يوسف
يس
طيب. عبد الله بهروم،
Yes, دكتور موجود.
خالد باسودان، خالد باسودان،
يس دكتور.
ريان كعكي، ريان كعكي، ريان كعكي، محمد سليم، محمد السليم. طيب who's absent؟ عندي معايا absent سلطان حسن البن سعد، عبد العزيز الراشد، حاتم الرويس، نواف الشهري، وريان كعكي.
Doctor, you haven't called my name.
What's your name, brother?
زياد بحلس.
زياد بحث. I called you and made you present. طيب ريان كعكي no mic. طيب ريان كعكي no mic. Okay طيب. Okay guys, see you next time. Till then, take care. يلا السلام عليكم.